The first gas law that we're going to look at involves pressure and volume. And if you think about this logically, hopefully it makes sense to you that when you increase pressure on something, the volume, the amount of space it takes up, decreases. So Boyle's law says that if the number of particles and the temperature are held constant, then increasing the volume causes a decrease in pressure. When you increase the volume, the pressure decreases. This is an inversely proportional relationship. When one factor goes up, the other factor goes down. The units for pressure or volume, when you use this relationship shown, must be consistent. So if you measure pressure in atmospheres, if you measure the first pressure in atmospheres, then the second pressure must also be in atmospheres. So this relationship that Boyle came up with is the pressure and the volume multiplied together for the first condition must equal the pressure and the volume, pressure times the volume for the second condition, so long as you're not changing the number of particles or the temperature. Charles' law. Charles said that if you're holding the number of particles and the pressure constant, then increasing the temperature causes an increase in volume. Increasing the temperature causes an increase in volume. And you might have experienced this if you've ever purchased a balloon from a store, and then you go outside on a hot day, and sometimes the balloon will explode because it increases in volume to the point where it can't, the balloon can't hold it anymore. Or the opposite, if you purchase a balloon and you go outside on a cold day and the balloon kind of gets shriveled up because the air inside of the balloon decreased in volume. This describes a directly proportional relationship. When one variable increases, the other variable increases also in a linear relationship. So this is a straight line relationship. When you use this relationship, so Charles' law is represented by volume divided by temperature for the first condition equals volume divided by temperature for the second condition. When you divide by temperature, that temperature must be in Kelvin. You must, if you're given degrees Celsius, you must convert it to Kelvin before trying to do this calculation. The units for volume aren't so important so long as you're consistent. If you use liters at the beginning, you'll get liters at the end. If you use milliliters at the beginning, you'll get milliliters at the end. So just be consistent in your units for volume. So notice the difference between this and the previous slide. Here we've got a straight line, directly proportional relationship, as opposed to the previous slide when we had an inversely proportional relationship. Gay-Lussac. His law states that if the number of particles and the volume are held constant, again, it's always important to keep these number of particles constant, and there's always one other factor held constant, then increasing the temperature causes an increase in pressure. Increase in temperature causes an increase in pressure. So this is, the balloon would not be a good example here because a balloon can change its volume. Here we're talking about a rigid container that can't change its volume. So you might think about something like a popcorn kernel. Okay, a popcorn kernel doesn't change its, or tries not to change its volume, but then you heat it up in a popcorn popper and it explodes. That's an example of increasing temperature causing an increase in pressure, which can eventually, if the container fails, cause an explosion. When one variable increases, the other variable increases. So this is an example of a directly proportional relationship. Again, when we follow this relationship that involves pressure and temperature, our temperature must be in units of Kelvin. This relationship only works if temperature is in Kelvin. The units for pressure are less important. You can use whatever units for pressure you want. but you must be consistent. So if your initial pressure is in atmospheres, then your final temperature will be in atmospheres. Again, we've got this straight line, directly proportional relationship, and Gay-Lussac's law is pressure divided by temperature of the first conditions equals the pressure and the temperature of the second condition, so long as number of particles and volume are held constant. If we put these three laws together, we get what's called the combined gas law, because we combined three laws together. So the combined gas law says that pressure times volume divided by temperature of the first condition equals pressure times volume divided by temperature of the second condition. Again, the units for temperature must be in Kelvin. The units for pressure and the units for volume can vary, but they have to be consistent between the first condition and the second condition. This law kind of takes the place of Charles' law and Boyle's law and Gay-Lussac's law, and it works for all gas problems that have a fixed or constant number of gas particles. So long as you're not changing the number of moles of gas particles, this law works. If you have a situation where one variable is staying constant, you can drop it. You can remove it from the equation. So before we look at some examples of how to use this equation to solve problems, in case you're curious and you want to be able to remember which law is which, I will not test you on this. But I came up with a mnemonic device which helps me remember, which is peanut butter vinegar can't taste good. And what this helps me remember is P stands for pressure, V stands for volume, T stands for temperature, B stands for Boyle, C stands for Charles, and G stands for Gay-Lussac. And if you kind of go around the circle like that, you see that the letters go in that order. And this helps me remember that Boyle's law involves pressure and volume. I see that Charles's law involves volume and temperature, because it's between the V and the T. And then Gay-Lussac's law involves temperature and pressure. So if you're wanting to remember which one's which, that's how you can do it. Also notice that remembering this mnemonic helps put P and V and T in the correct place for the combined gas law. So P and V are on top and T is down below. So that also helps you remember which variables to multiply and which variables to divide. So let's look at an example. A gas occupies 7.84 cubic centimeters at 71.8 kilopascals and 25 degrees Celsius. Find its volume at standard temperature and pressure. We haven't talked about standard temperature and pressure yet, but standard temperature and pressure, or I talked about standard temperature, is 0 degrees Celsius, which is the same as 273 Kelvin. And standard pressure is 1 atmosphere of pressure, which is the same as 101.325 kilopascals. So I like to always label my variables given to me in the problem. Cubic centimeters is a measure of volume, how much space something takes up. Kilopascals is a measure of pressure, and 25 degrees Celsius is a measure of temperature. Now, it's not the correct units for a gas law problem. I need to convert these to Kelvin, but I can do that just by adding 273, and then I get a value of 298 Kelvin. So this is my temperature value. So if I'm making a table of what I know and what I'm trying to find out, I know that my volume number 1, my starting conditions, my pressure number 1, and my temperature number 1 are 7.84 cubic centimeters, 71.8 kilopascals, and 25 degrees Celsius, which is 298 Kelvin. I want to calculate what is volume 2 when my pressure is going to be 101.325 kilopascals and 273 Kelvin for temperature 2. So I set this up. Pressure 1, volume 1 divided by temperature 1, pressure 2 times volume 2 divided by temperature 2, and this is the problem that I set up. Pressure 1 was 71.8, volume 1 was 7.84, and temperature was 298. Pressure 2 is 101.325. Temperature 2 is 273. So now this is a question of algebra, solving this equation to solve for volume 2. So if I do this multiplication and division on the left, I'll get 1.889. If I do this division on the right, I'll get 0.3712, but I still have volume as my variable on the right-hand side. So now I want to divide both sides of the equation by 0.3712, divide by 0.3712, and I will get as my final answer 5.09 cubic centimeters. Now notice when I divide away, I also divide away the units, so kilopascals per Kelvin, kilopascals per Kelvin. So the kilopascals per Kelvin cancel out, and that's why the units I'm left with are cubic centimeters. Just as a refresher, it does not matter what your units for pressure and your units for volume are, so long as you're consistent on both sides of the equation. But it does matter what your units for temperature are. They must be in Kelvin. This was an example of using the combined gas law. We used all three variables, the pressure and the volume and the temperature. This equation works just as well, even if you don't have all of that information. So let me do some examples with that. Here, my volume is 100 milliliters to 3 sig figs, and my pressure is 150 kilopascals. I need to find the volume, this is my unknown, at 200 kilopascals. This is pressure number 2, to make it different to pressure number 1. So, if I remember the combined gas law, this is the setup, but notice nowhere on here did I have any temperatures. Therefore, I can cancel out the temperatures and not use them at all. So I'm really just left with P1 times V1 equals P2 times V2. I don't have to memorize it as a separate equation. I just memorize one equation, the combined gas law, and I adjust it to my particular situation. This is really an example of Boyle's law as it stands, because it relates pressure and volume. So I plug in pressure 1 and volume 1, pressure 1, volume 1, and I plug in pressure 2, but I have to solve for volume 2. This is a question of algebra now. Multiply together and divide away the 200 so that I get volume all by itself. And you get volume equals 75.0 milliliters. Again, including those units here actually helps you see that these units disappear and cancel out, and the kilopascals on this side disappear and cancel out, and that's why you're left with milliliters as your final units.